excited to be here. I'm Jim Posen, and I'm going to be talking about some work we're doing at Irreducible and a cryptographic scheme called FRI-Binius. So Irreducible is a cryptographic acceleration company. We're focused on producing the fastest technology for producing verifiable computing and producing snarks and ZK snarks. What do I mean by cryptographic acceleration? Well, we're looking at how to improve performance of ZK snarks using both cryptographic techniques, high-performance software engineering techniques, and hardware engineering techniques, and combining all of these into an optimal system. So we think both that we can apply hardware acceleration to make our software faster, but also that we can adapt our cryptographic schemes to be amenable to hardware acceleration in the first place. This is a process known as hardware-software co-design. And it is one of the motivating factors for Binius, which is a hardware-friendly proof system that we've researched and developed and are developing at Irreducible. So I want to quickly talk about where we are with verifiable computing and ZK proving in 2024. It's the progress that we've been able to make in the past 5 years has been incredible, and Anna was giving some of the milestones in her presentation, but essentially we can now prove generic virtual machine computations, like we can prove EVM execution and RISC-V processor execution and WebAssembly execution with zero knowledge instead of writing custom circuits for every application we want. And this is really fast. We can run RISC-V processor, or we can emulate RISC-V execution with projects like SP1 at 100 kilohertz on a single server, which is far from where we are with native performance, but is really pretty remarkable. What it's taken to get here is we now live in a world where proof recursion is really efficient, and we can build sophisticated architectures that involve many layers of proof aggregation, where, for example, in the Polygon ZK EVM, we're going to prove ZK EVM, or we're going to prove EVM transactions at the top in these leaf nodes, and then go through several layers of recursion to end up with a single, very small and easily verifiable proof that goes on-chain onto the Ethereum L1. There's been a lot of cryptographic innovations it took to get here. We have hash functions that are designed for ZK proving. We have new protocols that are much faster than what we used to use for reducing the amount of committed data. We have lookup arguments, and there's a really important optimization called small field techniques that I'm going to drill into here. Anna mentioned that Plonky 2 was this really remarkable and somewhat revolutionary project that popularized small field snarks, and it came out in 2022 and actually demonstrated sub-second proof recursion, which hadn't been done before then. And one of the big unlocks was small field techniques, which at the time was mostly limited to Starks and hash-based snarks. So broadly, we can build snarks out of elliptic curve assumptions and out of hash-based or constructions using hash functions and linear error correcting codes. And the Stark protocol, which is what Plonky 2 is based on, and so the Stark protocol uses the FRI protocol, which is what Plonky 2 is based on. It used a 64-bit field, which fits within a single machine register on a 64-bit CPU, which modern CPUs are. And now modern Starks will use 32-bit fields. For reasons I'll get into later, we haven't been able to go smaller than 32 bits until our work Binius. But why are these so much faster? Well, they fit within a single machine register, whereas elliptic curves generally require 256-bit primes, and it takes many, many machine instructions to do a single field operation, whereas with small prime fields, you can do this in a couple of cycles. And with small field Starks, we can recursively verify these hash functions designed for prime fields very cheaply, like the Poseidon hash function. And this technique has been so popular that many proof systems, including Starkware's new proof system, RISC-Zeros, and Matter Labs, Boojum, all use small field techniques. I want to talk about why snarks are so slow today. So there's, to oversimplify, 4 steps that we need to do in order to compute a snark. The first is you're going to generate the witness, which is basically a trace of the machine that you're trying to execute. And this is not particularly slow, but it's a little tricky to parallelize. The second step is called committing the witness, which is where we're going to take that trace data. We're going to apply an error correcting code that you can compute with a number theoretic transform, an NTT, and then we're going to do a Merkle hash over that data. This is fairly expensive. The third step is called the vanishing argument. There's a couple of ways to construct it, but essentially this is many finite field polynomial evaluations done over and over and over on different points, and so it reduces to lots of finite field multiplications. And the last step is called the opening proof, which is sort of the fanciest in terms of cryptography, but actually doesn't contribute that much to proving time. So we can look at the actual profiling data from running a modern Stark, which is Plonky 3, to verify many Ketchak hashes. So this is the results when we use a Stark to verify the execution of enough Ketchak hashes to hash about a megabyte of data. And this, on a single thread on a modern processor, will take, I guess, between 40-some and 80-some seconds. On the right, we have the execution when we're using a recursion-friendly hash function like Poseidon, and on the left, we have the execution when we're using a CPU-friendly hash function like SHA-2. And there's a huge gap here because the recursion-friendly hash functions are just much, much slower than SHA-2, which even has custom CPU instructions. But what we can see is that the time to commit the data and do the vanishing argument dominate our proving time. And so we looked at how we can bring down the time to commit data, especially. One thing that we see when we look at why Plonky 3 is so slow is that the data that we're applying error correcting codes to and Merkleizing uses 32-bit field elements, but only 1 bit out of most of those field elements is actually meaningful data. Most of the field elements that we need to compute over have only 1 bit of meaningful data or 16 bits. And so this just sort of out of the gate looks like a 32x loss in efficiency where we have to pad up our 1 meaningful bit to 32 bits. And that's what we're attempting to capture by moving to even smaller fields. So at Irreducible, we asked, how can we move to even smaller fields? In fact, the 1-bit field, which is called F2, it has the values 0 and 1. Can we use this without paying the price of padding our field elements up to 32 bits while still using FRI techniques? Briefly, I'm going to summarize how binary fields are different from prime fields. So prime fields are a type of finite field that we're more commonly used to. These are the integers modulo some prime number. You can pick any prime numbers, but let's say a 32-bit prime number, you just take the integers modulo that, and addition is integer addition, and multiplication is integer multiplication, and then you need to apply this modular reduction process, but they behave in a pretty normal way. Binary fields you might be less familiar with. For any number k, you can define a binary field over a k-bit string, and field addition will amount to bitwise XOR, so it's entirely bitwise. And multiplication is kind of weird. It's actually polynomial multiplication, but the thing to understand about it is that it's carryless. So when you do integer multiplication, if you think back to grade school, you need to propagate the carries as you're doing your multiplication, whereas with binary field multiplication, you don't need to propagate carries, and it's much more efficient in hardware, and we'll get to the hardware numbers at the end of this presentation. So I'm not going to describe the math in great detail, but I want to show you how these binary fields behave. So we can take a string of 128 bits and interpret it as a 128-bit field element. But using this tower construction, we can create a family of binary fields called a binary field tower, and actually interpret those same 128 bits as a vector of 4 32-bit field elements, or as 16 8-bit field elements, or as 128 1-bit field elements, and that's just a memory cast on the same underlying bits. But this becomes an extremely useful property as we're trying to construct snarks that kind of maximize the information density and also match our finite field data types to the data types that we would have in a normal CPU, like bytes and 32-bit words and 64-bit words. If you look at the research, these are actually extremely efficient asymptotically as well. We can use Karatsuba techniques to get very fast multipliers and even finite field inversion. And so Binius is the result of our work to apply these techniques using towers of binary fields and be able to do snark computations without paying this embedding overhead that we saw in Plonky 3. So we had to combine a number of techniques, some that were known before this work and some original research. And it's using a type of snark proving system based on the sumcheck protocol, which differs from how Starks work and how Plonk works typically. And we also have a new polynomial commitment scheme that generalizes breakdown and FRI. There were several other innovations in the research we put out, which is covered in these 3 papers. So now I'm going to move on to the core polynomial commitment, which is how we're able to capture so much of this efficiency. And it's based on the FRI work. It actually draws from 3 different papers in different ways. So the FRI-Binius polynomial commitment scheme is based on the FRI protocol, which is from 2018 and underpins Starks. And actually, the original Stark protocol worked for binary fields. It did not talk about binary towers, but in our work, we had to do some additional work to make it compatible with our multilinear prover. The second contributing research, or second line of contributing research, is basefold, which gives a multilinear polynomial commitment scheme using the FRI protocol. And the third is an algorithm for efficiently doing Reed-Solomon error correcting encoding in binary fields. So this slide, I'm going to talk about how the FRI protocol works and how the polynomial commitment scheme works when you have very large fields. So we're going to start with a polynomial with 2 to the L coefficients here. And the first thing that we're going to do to commit this polynomial is we're going to apply a Reed-Solomon error correcting code. Now, Reed-Solomon codes are a very important type of error correcting code that have really good properties, and they're pretty simple to describe. The idea is that if we have a message with, say, 10 coefficients, we can evaluate that polynomial with 10 coefficients at 100 points, and that gives us redundancy. That gives us redundancy for the purposes of error correction. This is actually extremely similar to how Shamir's secret sharing works, where if you do that process, you could end up with 100 shares and a recovery threshold of 10. So same underlying idea, gives us Reed-Solomon error correction codes. And we want to check that not only is this a Reed-Solomon code word, but also that there's an inner product relationship defined on it. And the way we're going to do that is we're going to fold it and try to verify the same claims for a code word of half the size. So we're going to start with, something with, say, 1,000 coefficients and say this thing is a Reed-Solomon code and this inner product relation holds if and only if the same properties hold on something with only 500 coefficients. And we're going to keep doing this folding using an interactive protocol between a prover and a verifier. And it was incredibly shown in the early 90s that actually this setting of having a prover and a verifier interacting gives the ability to verify extremely difficult to verify relations. And that result, which was like a landmark result, was shown using the sumcheck protocol, which we also use in our scheme here. At the end of the day, when you fold this enough times, you're going to end up with a very small code word that you can check directly. This is how FRI works at its core. The problem for using very small fields is that, as I said, Reed-Solomon error correction depends on evaluating a polynomial at many points. And so if your field only contains 2 points or 256 points, how could you possibly evaluate it at more than 1,000 points? That means you need a field that's big enough to cover the size of your code word. And so that is why it's typical in these snark schemes to use a large prime and to pad your small coefficients into larger field elements, just so that you can work in this larger field. To the contrary, what we try to do is, instead of taking a polynomial with small coefficients like zeros and ones and padding them to 128-bit field elements, instead we're going to pack them into a single field element that contains all of those bits but are a single element. And this is using the same ideas as how the binary fields that I showed could be interpreted as many different field elements of different sizes at the same time. So in this case, we're going to take many different coefficients that are bits and pack them into a single coefficient or a smaller number of coefficients that have many bits inside of them. And we're going to skip ahead one slide here, come up with a construction where we can use the FRI protocol over a big field to do a polynomial commitment for a tiny field like f2 or an 8-bit field. And the idea is we're going to take the problem of a polynomial commitment for f2 and use the sum-check protocol to reduce this to a problem of applying FRI for a much larger field. I'm not going to go into too many of the specifics here, but essentially we've identified a mathematical data structure called a tensor algebra that embeds the field extension of 128 bits in both a horizontal and vertical direction. And this mathematical notion directly encapsulates the notion of packing that we need to do this sort of small field to large field reduction. This is a table of some of our initial results of implementing this scheme. So we compare against the Plonky 3 protocol. And what we can see is that when we are committing coefficients with a single bit, we're about 10 times faster than Plonky 3, precisely because of this embedding overhead phenomenon, where they have to pad field elements that are 1 bit up to 32 bits. This is the results of using the FRI-Binius protocol to create a snark that also verifies the same number of Ketchak hashes. And what we can see here is that the time to commit the data has shrunk dramatically because the amount of data that we have to commit is so much smaller. The vanishing argument is still fairly expensive, and at the end of this presentation, I'm going to talk about some research ideas on how we're going to bring that down. The final thing I want to touch on is why Binius is hardware friendly. And this goes back to the properties of binary fields that I was talking about and the fact that multiplication is carryless. So at Irreducible, we use FPGAs to accelerate our computations. FPGAs are basically reprogrammable hardware. So you have a native digital circuit that can verify that can perform some computation. And if we look in this table, we can see that to compare a very efficient 31-bit prime to a 32-bit binary tower element, the binary tower element is about 5 times more efficient when you take into account both the number of logic gates that are required to implement this and the clock frequency that you could run this at. We can also look at the hardware resources required to perform a 256-bit prime field multiplication, which are required for elliptic curves, and it's, I think, 20 times more expensive than our 128-bit tower multiplication. The same sort of efficiency holds when we look at larger operations than just multiplication. So when we look at the number theoretic transform that is part of the error correcting coding, which is typically a bottleneck, we see that doing the NTTs over a binary tower is also something like 5 times more efficient than doing it over a 32-bit prime field. And when we look at the complexity, the hardware complexity of a hash function computation for a recursion-friendly hash function, this also is much, much faster using a binary field than a prime field because of the hardware efficiency of binary fields. So our work is far from done. We have had a lot of research ideas and are implementing this in an open source Rust project called Binius. And at the same time, Irreducible is developing custom hardware accelerators. These are some of the research topics that we're focused on now. So how can we bring the vanishing argument time that I showed in our graph down from something that's large to something very small by capturing the same efficiency of small fields that gave us benefits elsewhere? The rest, in terms of optimizing the PCS, this is just engineering work that we need to do to apply known optimizations for batching. We are also working on a verifiable virtual machine that can do proof recursion really efficiently, and that's how we're going to create, large-scale useful architectures like the Plonky or the Polygon ZK VM that I showed at the beginning. We're working on FPGA accelerators for binary fields and a more ergonomic constraint system API so that this can be useful to more developers who want to build their own ZK VMs on top of Binius. So you can follow our progress on our website or on Twitter or at the binius.xyz, which will link to the repo. And thank you very much.